Welcome back to the Deep Dive. Today we're getting into something called spontaneous symmetry breaking, SSB for short.
Right.
It sounds pretty abstract maybe, but it actually shapes, well, everything, from magnets right down to the particles inside you.
Exactly. And we're going to explore this through the work of Yoichiro Nambu, a Nobel laureate.
His Nobel lectures are source, right?
That's right. A direct look at his thinking. His ideas, starting from superconductivity, they really revealed this hidden mechanism that gives particles mass. It fundamentally changes how we see the laws of physics.
Okay, so spontaneous symmetry breaking. Let's maybe use a picture, a simple one. Imagine you've got this perfectly straight elastic rod standing upright. Okay. It looks the same all around, right? Yeah. Rotational symmetry. But what happens if you push down on the top, harder and harder?
Well, it's going to bend, obviously.
Right.
And when it bends, it has to pick a direction, any direction, but it picks one. And suddenly, looking at it, that rotational symmetry is gone. It doesn't look the same from all sides anymore.
The symmetry is broken.
Well, yes and no. The bent rod has lost the symmetry. But the underlying laws of physics governing the rod, they still have that rotational symmetry. The potential is still symmetric. That's the core idea of SSB. It happens everywhere.
Okay, that makes sense for a rod. But how does this, translate to the quantum world with tiny particles, lots of them?
Yeah, it's a bit different, but the principle holds. In quantum mechanics, especially when you have many interacting parts, like in a material, the individual bits might have choices, freedom. But their interactions, their collective behavior can force them into alignment.
Like everyone in a crowd suddenly looking the same way.
That's a good analogy, yeah. And once they're all aligned, it's really hard to get all of them to flip the other way together, even if one person turning costs almost nothing.
So the overall symmetry seems lost.
It appears lost locally, yes. It points towards what we call a phase transition. You see it in magnets, ferromagnets, picking a north-south direction, they lose rotational freedom, or crystals, where atoms lock into place, breaking the freedom to be anywhere translational symmetry.
Interesting. And you mentioned temperature.
Ah, yes, crucial point. Usually if you heat these systems up enough, the symmetry gets restored. The magnet loses its magnetism, the crystal melts. That thermal energy overcomes the collective alignment.
Got it. So how did Nambu connect this idea to fundamental particles, to their mass?
Okay, so the big moment for Nambu was around 1956. He'd been to a seminar on the BCS theory of superconductivity.
Right. Bardeen Cooper Schrieffer.
Exactly. And something bothered him. The theory worked incredibly well, but it didn't seem to properly respect something called gauge invariance, a fundamental symmetry principle in electromagnetism. His genius was to look at the energy gap in the BCS theory. This energy needed to break apart electron pairs, which is key to superconductivity, and realize it looked mathematically just like the mass term for a particle in quantum field theory.
Whoa. So superconductivity gap equals particle mass. How did that help with the gauge invariance problem?
Well, the apparent violation of gauge invariance, which is linked to charge conservation, was the problem. Nambu figured out that to fix this, to make the theory consistent, you needed a collective excitation, a sort of wave in the superconducting medium.
Okay.
And this wave, this mode, had to be massless. This is what we now call a Nambu-Goldstone boson, or NG boson. It essentially carried the missing symmetry information and restored charge conservation.
And then he applied this to particles.
Precisely. He took this mechanism and applied it to particle physics, specifically to something called chiral symmetry. It's kind of handedness for particles.
Like left-handed and right-handed.
Sort of, yeah. The underlying laws seem to have this symmetry, but particles like protons and nucleons clearly have mass, which seem to break it. Nambu showed that chiral symmetry could be spontaneously broken.
Ah, so the laws are symmetric, but the vacuum state, the ground state of the fields, isn't.
Exactly. And this breaking generates the nucleon mass and the associated Ng boson. He identified the pion, a known particle, as a likely candidate. It's not perfectly massless, but very light, which fits the picture of a slightly imperfectly broken symmetry.
That's huge. So this SSB idea is not just one particle. It ripples through the whole standard model, you said. How does it connect to, say, the Higgs boson?
It's absolutely foundational. Nambu's work on how these Ng bosons arise was critical. The next step, which others built upon, was realizing that if the symmetry being broken is a gauge symmetry, then the Ng boson doesn't appear as a separate massless particle. Instead, it kind of gets absorbed by the gauge field particles, giving them mass.
And that's the Higgs mechanism.
That's the core of the Higgs mechanism, yes. It's how the W and Z bosons, the carriers of the weak force, get their mass in the Weinberg-Salam theory, which unifies electromagnetism and the weak force. Nambu's SSB work paved the way.
Wow. And even things like why particles have such different masses.
Potentially, yes. Nambu speculated that maybe the universe went through several stages of SSB as it cooled down after the Big Bang. A hierarchy of symmetry-breaking events. Each time a symmetry broke, particles associated with it might gain mass or have their masses set. It could explain the sort of ladder of masses we see for fundamental particles, the mass hierarchy problem.
So just to pull this together, this one idea, SSB, it connects crystals forming, superconductors working, and particles getting mass.
It's incredibly universal. That's the amazing thing. You start with atoms forming a crystal lattice, that's SSB of translational symmetry. The vibrations in that lattice, the phonons, they are the NG modes. Those phonons can then mediate the electron pairing that leads to superconductivity, which Nambu analyzed. Then you look at quarks, the building blocks of protons and neutrons. Their chiral symmetry breaks spontaneously.
Giving us massive nucleons and nearly massless pions, the Ng bosons.
Exactly. It's this cascade, this tumbling of symmetries. As the universe cooled, phase transitions occurred, symmetries broke, and the fundamental rules governing interactions in particles, well, they changed.
It really shows how something that looks broken or imperfect on the surface, like mass itself, can actually arise from a deeper, perfectly symmetric set of rules that are just hidden.
Precisely. The symmetry isn't gone. It's just realized differently in the state of the universe we live in.
A deep dive indeed. It reveals these hidden connections between, everyday phenomena and the absolute bedrock of physics.
And it leaves us with a really interesting thought, doesn't it, for you listening? If so much of what we see mass structure comes from these fundamental symmetries being hidden or spontaneously broken, what other symmetries might still be out there? Perfectly intact in the underlying laws, but just waiting for us to find the conditions or the perspective to see them. And what new physics, what new understanding of the universe could that reveal?